U.S. Army Corps Engineering, TI 850-02, U.S. Army Air Force, AFMAN 32 11 25 1 March 2000. Technical Instruction, Railroad Design and Rehabilitation, Chapter 6. Chapter 6, Track and Roadway Design. Roadway. The definition of roadway is also called the right-of-way, the strip of land containing the track, ditches, and other facilities needed for the operation of the railroad. Railroad width. The railroad width may be enough to accommodate the trackside, ditches, portions, embankment, cut slopes, parallel surface roads, other structures and facilities necessary operation of the railroad. The roadway must also sufficient clearance between the track and adjacent structures and covered by the Chapter 6 paragraph figure 6 through 6-7 indicate the width required for the basic structures. Okay, 6-1, typical cross-section of a tangent track. It shows that on the side you have the 1-3 and 1-3 right angle triangle at the compacted subgrade with an 18-inch margin to the top of the ballast, which has a 2-to-1 ratio on a parallelogram theorem. 6 inches from the ballast and to the tie end, which is also the ballast is a slope of 2 to 5% typical. The ballast seen in compacted subgrade under the ballast under the tie. The depth of the ballast is to be usable depending on the subgrade traffic strength, traffic density, wheel loads, recommended structural analysis to determine the appropriate depth of each site. Minimum basic thickness of 8 inches below the bottom of the tie, and cut fills according to the local conditions. There is from the center of the tie to the inside of the rail is 2 feet 4 foot 4 1/4 inches from the center of the tie to the railhead inside of the railhead, with a slope of off the grade of the side of the tie at 2.1 and slope 2.5% at the top of the tie to a drainage ditch which has a 3-to-1 parallelogram theorem with a 1 foot minimum grade ditch. Alright, this is a typical cross of a sub-ballast layer tangent track. You see the sub-ballast notes. The depth of the ballast section will depend on the subgrade strength, traffic density, wheel loads. Use recommended structural analysis to determine appropriate depths for each site. Minimum thickness of ballast sub-ballast is 10 inches below the bottom of the tie. The thickness of the ballast and sub-ballast may be varied obtaining the best structural economic design while meeting the minimum thickness requirements. Cut and fill according to local conditions. Once again, from the center of the tie to the inside of the railhead is 2 foot 4 1/4 inches centered halfway in your 56.5-inch gauge. With a 6-inch off to the side of the tie to the slope of a 2.1% on the top ballast, which hits another sub-ballast with an 18-inch type off to the side. To one side, there's a 3-to-1 slope off the compact grade subgrade, which is 20 inches minimum, 20 foot minimum across the center of the tie, which goes down into a drainage ditch with a 3-to-1 parallelogram hypotenuse and 1 foot with a 3-to-1 inch typical cross section sub-ballast layer. Typical cross-section curve track. This shows the depth of the ballast will depend on the subgrade of the traffic density, wheel loads. Use recommended structural analysis to determine the appropriate depth of each site. Minimum thickness of 8 inches below the bottom of the tie at the inside of the rail of the curve. Other curves of the 6 degrees greater than the ballast should be the width of 8 inches and should be used and cut and fill in according to local conditions. From the center of the tie, you have a 20-foot minimum compacted subgrade with a typical, which on top of that was the ballast of 8 inches below the bottom of the tie, or curves 6 degrees. The ballast width of 8 inches should be used for the curves. So 8-inch ballast with a slope of 2.1 off the side of the rail with a 2 6 inch minimum on the end of the tie. From the center of the tie, a 2 foot corner, 4 1/4 inch or a 56.5 inch gauge, and then into the drainage after the 20-foot minimum off the side of an 18-inch minimum slope to the tangent curves sectional geotextile drainage, 3 1/4 slope, 3 and 1 hypothesis slope with a 1 foot minimum. Okay, typical cross section of a sub-ballast layer. 1. Depth of the ballast will depend on subgrade traffic density, wheel loads used, recommended structural analysis to determine appropriate depth of each site. Minimum thickness of the ballast sub-ballast is 10 inches below the bottom of the tie. Thickness of the ballast subgrade of the varied to obtain the substructural economic design while meeting minimum thickness requirements. Other curves of 6 degrees or greater ballast width of 8 inches should be used. Cut-off fill according to local conditions. Same thing from the center of the tie, but it's slightly raised. This varies from 2 to 5%, and the minimum of the top and the sub-ballast slopes at 2.1, with 18 inches off the side of the top ballast to the sub-ballast into the drainage, which has the 3-to-1 ratio. At the gradient with 1/4 gradient minimum. Same thing. Typical railroad is 2 1/4 inches by 6 inches. 10 minimum sub ballast. Typical minimum of 20 feet on the compacted subgratis fill. Typical cross section track adjacent service road. This service road is 11 foot on the top of a compacted subgrade of 30 minimum with the off the side of the service road. It's granite water runoff at 3 1/4 fill. From the service road, you go up a slope of 2 1/4, slope of 2-to-1. From the 6 inches from the tie to the railroad center of the tie. 2 1/4 inches, 1/4 inch to the inside head of the rail, 6 inches down the sloping, 2 1/4 on 3-and-1 and 3-and-1 minimal. Depth of the ballast depending on the subgrade traffic density, wheel loads, recommended structural analysis to appropriate depth of each site. To be used where service roads are required. Service roads turn around require every 2,000 feet. Service roads turn around required every 2,000 feet. Sub-ballast will be a minimum of 4 inches deep, compacted at least 90%, and the CE 55 maximum dry density. Cut and fill according to local conditions. Typical cross section of tracks geotextile. This shows the ballast. The depth of the ballast section will depend on the subgrade strength, traffic density, wheel loads used, recommended structural analysis to determine appropriate depth of each site. Minimum thickness of the ballast subgrade is 10 inches below the bottom of the inside of the rail of the curve, which are area gradation of 5 to 12 inches. Minimum thickness or graduation of 4 to 4A. Geotextiles to meet the requirements of CEGS 02274 and geotextiles insulation curves will be similar. This is typical not to scale. 20-foot minimum on the compacted subgrade. Above that, with a minimum graduation of 5 to 12 inches thickness of ballast underneath the center of the tie. 2 foot 4 1/4 inches from the center of the tie to the inside of the railhead. 6 inches off the end of the tie with a slope of 2-to-1 ratio, meeting an 18-inch flat plateau on the compact grade, which grades on a gradient of 1 to 3. Typical cross section of sub-ballast layer track with geotextiles. Depth of the ballast will depend on subgrade strength, track density, wheel loads. Using recommended structural analysis to determine appropriate depth of each site. Minimum thickness of the ballast. Sub-ballast is 10 inches below the bottom at the inside of the rail. The curvature with an area of the graduation 5. 12 inches minimum depth of graduation of 4 and 4A. The thickness of the ballast sub-ballast may be varied to obtain the best structural economic design while meeting minimum thickness requirements. Geotextiles meet the recommended requirements of CEGS 02274. Geotextiles installation on curves will be similar. From the center of the tie is 2 4/4 2 2 foot 4¼ inch to the inside of the railhead, with 6 inches off both sides of the tide, with a slope of 2 to 1 on the top of the ballast, meeting a sub-ballast plateau of 18 inches to 3 to 1 off the compacted grade, typically 20 foot minimum with 4-inch minimum geotextile subgrade. C. Snow alliance. In areas where snowplow, additional road width and ditch width may be useful to provide sufficient rooms for snowplow for the track. 2. Grades and track profile. Grades, Chapter 3 grades, gradient criteria for main running tracks. Chapter 8 gives the gradient criteria for the terminal areas. Vertical curves. Vertical curves are required for transition between different grades. Transition to different summits, zags. Here are some summits. Refers to the convex curves using ascending grade. Changes flatter grades. Descending grades change the steeper grades, where an ascending grade to a descending grade sags, and concave curves are curves when ascending grade changes the steeper grade. The descending changes the flatter grade, where a descending grade changes the ascending grade. Note, it is best avoided the location of the turnouts and vertical curves. Table 6.1 shows recommended transition rates between grades. The length of track required for these transitions is determined in for the equal equation 6.1. L, the length by gradient 1 by gradient 2 in the radius divided by the radius times 100. Submits and sags. 0 to 1, submits, 0.05 sags. Average rate of speed will exceed 15 miles an hour right away. The length is ample. 2%, 0.2 or 0.1 slag. Average rate speeds will not exceed 15 miles an hour when transition length. A summit of 0.3 or sags of 0.15. Maximum rate where speeds exceed 15 miles per hour. Summits of 0.4, 0.2 minimum rate of speed will not exceed 4.0. Notice that your summits are half as big as the sags, and the summits are half as less as of the sag summit. Track profile. Either on either the main running tracks and terminal tracks, rolling profile, frequent changes in the gradient of the roadbed of the final structure, top of the rail. Evaluation is undesirable. The criteria in the table 3.2 should be followed in maintaining acceptable smooth track profile. For auxiliary gradient, given in Chapter 8 of the paragraph 3, may be used in length. L is the length of the track required of the vertical curve. Gradient GM1, slope of the 2 adjacent grades, where ascending the grades have positive value, descending of the grades in the negative value. The rate is the change in the grade of the 100 foot of the running tracks in Table 6.1 of the terminal tracks at the Chapter 8 and paragraph 3. Once again, that is length over the gradient minus the gradient adjacent gradient divided by the rate of the length of 100 foot rate of change over 100 foot. Horizontal, that's your slump or sag. Now, 3 horizontal curves. Definition. Railroads are laid out of the circular curves using core definition. Curves are measured in degrees and indicated in the equation 6.2. Alright, D is equal to 5,730 divided by R. The degree of curve is decimal degrees, equal to 5,730 divided by the radius of the curve. Design criteria. Design categories of the curves of main tracks are shown in Table 3.3 of the terminal, also used in Chapter 8 and Paragraph 3. During the design of the major track projects, the recommended that the practical axis in curve about 10 degrees for the main tracks and 12 degrees in the terminal areas reduced below these limits. Minimum tank length of the reverse curve. The curves different directions immediately follow each other. Reverse curves. These are most length of the tangent curve track between the two curves to avoid the train operating difficulties. The minimum tangent length between the reverse curves are: a 0 to 60 curve has a minimum tangent length of 60 feet. 60 to 12 is 100 feet minimum length. Super elevation. For either new design or major rehabilitation, other railroad curves should be evaluated above the inner rail mount shown in Table 6.2. Design should not call for combination of speed and curvature that fall below the bottom step ledger in the table. 2. Full super evaluation must be approved by the entire curve for the curves in 1 inch. The super evaluation may be run out and transitioned back into the level in 40 feet of the tangent and beginning into the curve. When the super evaluation is more than 1 inch, spirals were provided at each end of the curve. Spirals, when using spiral transition curves, will design as shown in Chapter 5 of Part 3 of the REMA manual. The super evaluation will uniformly increase to 0 as beginning in the spiral at the tangent to the full evaluation of the end of the spiral where curvature is reached. Alright, let me back out of this. This shows a degree of curvature. The note is the table entries are super elevation in inches. The design for the mile per hours that go from 10 to 15, 20, 25, 30 to 35 to 40. You can see that the half of a degree of curvature is at 1 point at the 1.40 miles an hour. 1.0 is 30 to 35 to 40. 1.5 is 25 to 30 with a 1.5 to 1.5 super evaluation curved miles per hour. Gradients, the degree of curvatures go from 0 to 0.5 to 12 on the degree of curvature. You can consider 8.5 to 12. All 4 through 12 in the degree of curvature has a 10 miles an hour basis. 3 through 8 curves have a 1.0 to 3 to 6, and 6.5 to 8.5, 1 to 5 design super curve elevation. The 20 miles an hour has a 2.0 to 4.0, 1.0 super evaluation required. Also with a 4.5 to 5.5, 1.5 super evaluation curve, 6.0, 1.5, and 6.5 to 8.0, 2.0 super evaluation curve required. The 25 miles per hour designing operation has a 1.5 to 2.0, 1.0 super evaluation, 1.5, 3 to 4 degree of curve, 2.0 to 4.5 to 6.0 has a 2.0 curve, and 6.5 and 7.0 have a 2.5 super evaluation curve track. 30 miles an hour, 1.0 to 1.5 has a 1.0 super evaluation, 2.0 to 2.5 has a 1.5 super evaluation. Now, 3.0 to 4.0 has a 2.0 super evaluation required, and 2.5 is a 4.5 elevation at 30 miles an hour, with 3.0 at 5 to 6 at 30 miles an hour. 1.0 at 35 miles an hour, 1.0 at 1.0, 1.5 at 1.5. This follows degrees. 2.0 is in 2.5. 2.0 and 2.5 has a 2.0 super curvature, while 2.5 has 4.0 has a 30, and 4.5 has a 3.5, and 5.0 has a 40. 40 miles an hour, the super evaluation required is 0.5. The degree of curvature and 1.0 have the 1.0 super evaluation required. 1.5 has a 1.5. 2.5. 2.0, 2.0, 2.5, 2.5, 3.0, and 3.5, 3.0 super evaluation required. Driving speed at 40 miles an hour. The 4.5 has a 4.0 super evaluation curve at 40 miles an hour. The spiral length will determine the equation of the 6-3. The length of spiral feet times 40 equals 40 times the full super evaluation in inches. These note that the entries in super evaluation is inches, so when I said 1.0, you got an inch or whatever. So increase the gauge by the very sharp curves. Where a curve is 12 degrees or more cannot be avoided. Finished track gauge should be as follows: curve range and curving range degrees and track gauge in inches. 12 to 14 inches, 56 and 5/8 of an inch. 14 to 12, 16, 56 and 3/4 of an inch. Clearance. Clearance will be checked for either new construction of the rehabilitation work, location of the position of all tracks checked and proper clearance before the final designated, prepared after construction complete, allowance to provide for future track support, surfacing, adding ballast and raising track. For small changes in alignment during the maintenance, be recommended minimum clearance at figure 6.8 and 6.3. Vertical clearance measured on the top of the rail. Horizontal clearance is measured in the center of the line of the track. This is a clearance diagram with a tangent of the track. 33 and a foot overhead wires exceeding 15,000 volts. 30-foot overhead wires at 750 and 1,500 volts. 28 feet overhead wires including 750 volts or less. The track center line, 9 foot to each side of the buildings. Starting at the right, going the overhead bridges obstruction from the building is the miscellaneous overhead obstruction conditions requires a 23.0 foot, which is the canopies are 8 foot and 6 foot offset offs, with the building entrance to the low platform is 18 foot and 23 foot to the overhead bridges and other obstructions from the low platform. 18 foot to the miscellaneous overhead obstruction continued conditions require less than 23 foot of an 8 foot. Freight platforms start at 4 foot and refrigerator platforms 3 foot 3 inches with an 8 inches off the platform, 5 foot from the center, track center, and 6.2 to the right angles, 8 foot to lower platforms, 8 foot across the plane across the top of the rail. Table 6.3, overhead side and clearance of the tangent track. Overhead wires are open supply 8 arc wires or service drops 0.75 foot at 0 to 750 volts, 28 feet, 750 volts to 15,000 volts, 30 feet, exceeding 15,000 volts, 33 feet. Overhead wires at 28 feet. Building entrances including engine housing at 18 feet. Overhead bridges at 23 feet. Overhead obstructions at 23 feet. Continued. Buildings at 9 feet. Buildings without platforms requiring materials 8 feet. Platforms, freight platforms at up to 4 maximum height of 6 foot 2 inches. Refrigerator platforms at 3 foot 3 inches at 6 foot 2 inches. Refrigerator car platforms at 3 foot 3 inches and 2 4 high inches. Low platforms less than 8 inches high. Engine house entrance 7 foot. Building entrance for the other engine house 8 foot. Canopies other than platforms canopy height of the greater than 18 feet or 8 requires an 8 foot clearance. The fencing, retaining walls, utility poles, and other obstructions have required clearance of 9 feet. Bridges 9 feet. Signs 9 feet. All loose palleted stacked materials 9 feet, and parked vehicles 9 feet. In curves, the side clearance will increase to 1 1/2 inches per degree curvature. C. State requirements. Each state has a local legal requirement to require railroad clearances. They are summarized in the table of Chapter 28. In Chapter 28, Paragraph 3.6 of an ARIMA manual, which states requires the rate clearance as figure 6.8 and 6.3. State requirements will be met. Curved track. For each degree of the curvature, side clearance increased to 1 1/2 inch over the figure of the 6 to 8 in Table 6.3. When an obstruction is located adjacent to the tangent track for the track begins the curvature within 80 feet of the obstruction, the side clearance should be increased to the amount shown in Table 6.4. Clearances increasing adjacent to curved track. Distance from obstruction of curved track 0 to 20 feet increases the clearance per degree in the curvature an inch, 1 1/2. Curvature obstruction of curvature track 21 to 40 feet 1 inch and 1 1/8 of an inch. 41 to 60 feet curved track obstruction 3 1/4 inch. 61 and 80 feet of the curved obstruction of curved track 3/8 of an inch. Minimum track standards. Minimum track standards. The minimum distance between the center lines and adjacent track is given in 6.5. The M1 tanks are handled with increased track spacing by 1 foot. Table 6.5 track center distances. Main track has a minimum distance center line of 15 feet. Side yarding track and minimum of 15 yard, and storage track 14 to 15 spaces. 15 foot space permits. Clear points of turnout ladders and crossing. Figure 6.9 shows how to determine local clearance points of turnout ladder tracks and rail crossing. As no piece of equipment may be left standing on the track with any part of the extending point past the clearance in the track toward the track junction. The clearance point will determine the usable length of the sidings, loading yard, and storage tracks. Clearance points will be marked by a 12-inch yellow bar painted on both sides of the rail base. If the derails are used, they must use derail equipment before it reaches the clearance point. This is the location clearance point. Will start at the top figure at from the left to the limits of minimum clearance between parked car and parked car, and a crossing of clearance marks at 12 inches painted on both sides of each side of the rail with a yellow 10 foot by 10 foot at the crossing from the side of the cars. So adjacent side of the cars. The clearance marking parallel lateral tracks have a 14 foot from center to center freight cars, except for on the mainline trackage where it was 15. The center lines are parallel spaced and limited minimum clearance. The clearance distance between the loaded cars must never be less than 3 feet. So you have 14 from the center tracks with the clearance marks of the parallel lateral tracks. Where M1 tanks are handled, increase the track centering spacing by additional 1 foot. Converging tracks. The adjacent crossing has 10 foot on the adjacent tracks on the parallel sides. Limits of minimum clearance converging tracks. 5. Track structure. Design objective. Among the various function track systems, distribute large concentrated wheel longitudinally, laterally, and vertically away from the wheel contact area on the rail surface. A well-designed constructed main track will be distributed in loads relatively uniform fashion, which will equip each component supporting its share of load. The role of the designer, selected track supporters so intended the wheel loads will be properly supported without overstressing any four main track system components, rail ties, ballast, or subgrade. Load distributions. As figure 610 shows, the wheel center over the ties directly beneath the load generally carries less than half of the wheel load. The remainder of the two ties on either side beneath the wheel pressure are distributed reduced approximately as shown in figure 611. With a real rail contact area of one half of an square inch, stresses are reduced to 60,000 pounds on top of the rail, about 10 psi. At the depth of the subgrade surface, which actually load pressure distribution vary with wheel load. Track design, track condition. 2 figures illustrate realistic cost of the good track. You see it has this half squint. The wheel railway contact area is a ½ inch. It shows the pressure on the other two ties is dropped by 0.5%. The 40% of 12,000 pounds. The preceding ties would be inside the next preceding size from the center of the wheel load would be 20%. As it rolls over, it lays off to 10% on 3,000 points of the ties, two more ties away. 611. Example: the vertical pressure reduction through the track. Wheel loads of up to 30,000 pounds on the top of the railhead of 660,000 psi rail. Tie plate is equal to 300 over 200 to 200 psi, and the tie at 40 psi, and the ballast at 10 psi to the subgrade. In the subgrade. Behavior under load. And it is important to note that while the track construction is relatively simple, its behavior under load is not. Improvement in increasing strength as one track component may cause the increased load of another. It is not uncommon for the improvement in increasing the strength of one track component cause an increased load of another. 6. Tracks design method. Computer program available. The computer program basic track design is called Track. It is available at the PCASE internet site http://pavement.west.army-mil/pk.html. Army Transportation System Center CNEWOEDTX is recommended. Manual design procedures. The computer programs are not accessible. Other computers unavailable. Design procedure. Paragraph 7 may be used an alternative disadvantaged method. However, very little data exists in the correlate the value of the track modulus or permits the individual rail support components, tie ballast, and subgrade. 7. ARIMA design procedures. 1995 modified. Applying the ARIMA method of military track. REMA method that leaves several choices of judgment open to the designer to meet according to situation policy. And like most of REMA's criteria, the method is oriented toward the commercial lines and carrying method of heavy track volumes, more than 10 million gross ton per year, operating medium high speed at more than 40 miles per hour. The guidance below is recognized by the military track operating relatively low track volumes at less than 5 million gross tons per year, a relatively low speed less than 25 miles per hour used jointed, rather than continuous welded or rail. For unusual cases where yearly traffic frequencies accepted exceed 5 million gross tons, design may follow directly into the Chapter 16 of REMA manual. Basic design. The REMA track design method is extensively field laboratory testing conducted between 1914 and 1940. Committing supervising testing evaluation was led by the Professor Arthur Talbot, University of Illinois, whose name was used referring to the tests and findings. One of the Talbot Committee's findings was that the subject larger number of loads, repetition, million groups of car, the greater vertical deflection under the loads, the fast track condition deteriorated. The data observation collected with the REMO developed a track design method limiting control of vertical rail deflection. Figure 6.12 illustrates general relationships between track deflection track performance over long periods. The design criteria for the section based on limited deflection on the main running tracks is 0.3 of an inch of an auxiliary and of auxiliary storage spur or light use of tracks is 0.4 of an inch. Alright, 6.12 shows the maximum track deflection long-term track performance. You see the grades get darker, and from the A to B you have 0.0 to 0.10% of the track load deflection under the load in inches, which means excessive stiff track, long-term performance. B is 0 to 10 to 0.25, track heavier construction, which will hold well under the large traffic volumes of less than 15 MGTs. C is 25 to 35, defined in white, and track suitable for low traffic is greater than 15 MGTs. D, the sliding auxiliary track of the traffic lines is D, which is between 33.5 and 4.0. And E is a track with determined quickly unsuitable occasional movements, which is 0.4 to past 0.5. The track will deteriorate quickly, only suitable occasional movements with cars less than 100 tons of capacity. Deflections do not include any play or loose between the track components. 4. REMA track design method used beam elastic foundation model. The model has the two components of the beam, which is rail elastic foundation that represents everything below the rail combined. The basic expression of the model relates to the three main variables of the load of the relay rail stiffness, track system, amount of vertical rail deflection is shown in equation 6.4. Y is the vertical rail deflection at point of inches. Equals P applied wheel load including contribution over the adjacent wheels and poundage. Times 64 times the stiffness of the rail, where times the stiffness of rail support of track modulus and psi to the cubed. Each variable of the ELU stands for module elastic steel of 30 times 10 to the 6 power of psi, vertical movement and inert rail selection in inches, for routed stiffness of rail support track modulus psi. In this equation, the EL represents the stiffness in the beam and the U stiffness of the elastic foundation. See the design load and wheel spacing. Since selecting the design wheel of table 2 based on the most common heaviest car expected in the travel over the track. Figure 16 shows two common wheel configurations. Most cars, the two-axle trucks, design wheel configuration is drawn with an average of 75 inches wheel spacing with a 140-ton series flat car for carrying an M1 tank over the heavy vehicles. And some 100 flat cars have three-axle trucks. These design wheel configurations in the drawing with a 60 inch wheel spacing. such as a car with 2 axles and a car with 3-axle flat car. The track is evaluated assuming that the wheel is centered over the tie of the adjacent wheel, that either the contribution load or the deflection stresses that occur to the 2 cars coupled together, referring to the maximum and ballast subgrades, will occur under wheels 1 and 4 continuing on the left. The maximum rail bending stresses will occur with the wheels 2 and 3. The wheels configuration is 613B, figure 613B. The maximum tie ballast subgrade loads occur under the wheels 2 and 5. The maximum rail bending stresses will occur at wheels 3 and 4. 4. The effective wheels farther than 100 inches design wheel negligible. D. Select track and modulus. The track modulus values in listed table 6.6 are suggested starting points of the design. The table track type of the main refers to the main running tracks. The auxiliary includes the siding, wise, loading, spurs, storage, interchange, and light use of the rail. The suggested design track of the module values design wheel loads of 1,000 pounds. The main track at 20 makes 3% increases with a 2% 15,000 pounds at 20 to 25, 25 to 30, 18,000 pounds, 30 to 35, 2,000 pounds, 35 to 40, 2,300, or 40, 45 pounds, 2,600, 45 to 50, 2,900. These the 1,000 pounds in 1,000 pounds. Auxiliary. The design wheel load ranges at 20 to 25, 1,200, 25 to 30, 1,300, 30 to 35, 1,500, 35 to 1,400, 1,700, 45 to 4,500, 2,000, and 45 to 50, 2,200. Select rail size. Using the equation 6.5 to determine the minimum rail weight height. WO, weight of the rail in pound per yard, equals to 315 minus 21,200 divided by P, the design wheel load poundage, divided by 1120 times A, impact factor, where A is one where design operated at a speed of 25 miles per hour less. A is 1.4 is design where operating speed is more than 2.5, more than 25 miles per hour, plus 67. Select the rail section in table 6.7 for equal greater weight of the calculated above. The rail selections are 101 ARAB and 112 100 ARAB at moment of inertia 1 inches, 41.3 inches to the square root of 4 to the power of 4. Section modules base V inches, 57 inches. 15.7 inches cubed. 1112R, 1115R, 1130R, 1132R, 1133R, and 1136R rail selections follow. I feel like skipping that, so determine the moment of loading coefficient. The moment of loading coefficient accounting for the effects of the wheel adjacent to the design. The wheel adjacent would reduce the rail movement and increase the tie of the ballast subgrade. Calculate x1 using this equation 6.1. The x1 should normally be ranged between 28 and 40. So x1 is the distance between the design wheel load and the point of the zero bending movement, which is between 28 and 40, equal to 82 times the radical of 4 over the vertical movement of an air rail selection inches of quartered stiffness of rail support track modulus PI. Determine the coefficients of CM and CD as follows. For the most design situations for the cars, the 2-axle, 3 axles of the movement railway coefficient cannot be taken at 0.8. Load coefficient of CD can be taken as follows. X1 equals to the 20 as the graduation from 28 to 30 to 32 to 34 to 36 to 38 to 40 by 2s. You see that the design wheel spacing for a 66 is 124 for 28, 130 for 30, 136 for 32, 134, 144, 136, 154. 38, 162, and 40, 170. Design wheel spacing for a 75 1.0, 108, 115, 122, 130, 136, 142, 150. Check rail bending stress. Using equation 6-7 to check the rail bending stress is within 32,000 pounds. The maximum flexural stress in PSI equal to 0.38 dynamic design wheel load poundage from table 2.2. cm, the moment of efficiency, times x1, the distance of wheel load point of the zero bending moment inches, and divided by ZB's selection of module railway base, table 6-7. Ties and tie spacing. Choose a trial tie spacing. Calculate a maximum rail seat loading using equation 6-8. QO, the maximum rail seated load in poundage, is equal to 0.39 times the dynamic design of the wheel load poundage from table 2.2 and times the CD load coefficient in adjacent wheels times tie spacing in inches divided by distance of wheel load point of the zero bending moment inches. To select the tie size, either 6 inches by 8 inches or by 8.5 inches, or 7 inch by 9 inch by 8.5 feet. Check the tie bending stress using the 6.9A, 6.9B, and FT. FT is equal to 1100 psi suggested limit. For 6 to 8 inch ties, the 1100 psi suggested limit is equal to the maximum rail seat loaded divided by 29. And then for 7 to 9 inch ties, the 1100 psi suggested limit is equal to the maximum rail seat load over 52. If the 1100 psi suggested limit is less than 1100, choose a large tie size and decrease spacing. Ballast and subgrade. Determining ballast surface stress, equation 610 to the equal to the PM. Ballast surface stress in PSI equal to 65 PSI is suggested. 65 PSI equal to the maximum railway seat poundage divided by the effective bearing area of the one half of the tie on the space of the square inches. For 6.8 ties, the effective bearing area is 270 square inches. For 7 by 9 inch ties, the effective bearing area is one half on the tie basis, equal to 312. If the ballast surface stress chooses the larger tie or decreasing tie space, select a design subgrade bearing capacity in accordance with the result of the soil testing, other data, and absent guidance. Design bearing capacity cohesive soil same as the unconfined strength. Determine ballast depth in equation 611. H is equal, the ballast depth in inches is equal to 50 times the ballast surface stress PSI divided by design subgrade bearing capacity to minus 10 to the square root to the power of 0.74 divided by 2.54. Subgrade. The subgrade stability track performance. The subgrade is prepared on earth only, which the railroad ballast selection tracks of a structure as built. The subgrade does not have sufficient stability. Will impose the two main track alignment profile and cross level. B. The soil investigation. Prior to the initial design of the track structure, geotextile investigation should be performed and made along proposed alignment to determine soil type, the strength, bearing capacity, location of groundwater tables, natural water content, compaction characteristics, and additional geotextile boring, laboratory testing, and engineering analysis will be required in the areas where the bridges and other special structures are to be constructed. Chapter 1, Part 1 of the REMA manual provides recommendations of the geotextile investigation. Design of the cuts of the fills, supergraded preparation. Chapter 1 and Part 2 of the REMA manual provides recommendation for design cuts, fills, and subgraded preparation. Table 125 of the REMA manual indicates soil types of the suitability as railroad subgrade. The track structure, design, bearing capacity, cohesive soils. The cohesive soils for the track expected to carry the usual military traffic level less than 5 million Gross tons per year. Designing bearing capacity of the track structure may set the soil unconfined compressive strength as natural water content for unusual cases where an annual track volume is projected by higher than 5 million gross tons. The 80% of the unconfined compressive strength may be used for the design bearing capacity. The soil stabilization information using soil stabilization of the design construction soil stabilized subgrades and presented in TM 5822-14 or AF Manual 1019. Especially in frost areas, soil stabilizer should be used in caution only after intensive laboratory testing, including frost susceptibility and testing and freezing through durability testing. 9. Frost design modifications. Frost heave conditions for frost season, raising soil design, growth in ice lenses and ice segregation during freezing. There are 3 basic conditions that must be present for the ice segregation to occur: the frost susceptible soil, a source of water, freezing temperature change, and other 3 conditions were the amount of the heave. Identifying frost susceptibility soils for designing potential ice segregation expressed by the functional grain or particle size. Most organic non-uniform soils contain 3% or more weight of particles smaller than 0.02 millimeters are considered frost susceptible. Gravel will grade to the high sands and silty sands, especially approaching theoretical maximum density curve. They contain 1.5 to 3% of the particles smaller than 0.02 millimeters should be considered possibly frost susceptible and subject to laboratory frost susceptible tests. Considerably segregation can be expected in the uniform sandy soils where greater than 10% is smaller than 0.02 millimeters. Illustrates a method of determining the frost susceptible soils. General method of determining frost susceptible soils. Water sources. Usually water sources will be underlying groundwater table of perch, aquifer, infiltration of the overlying layers. Frost depth. Frost track maintenance caused by reduced in design depth of frost below the top of the ballast at 60% of the experienced local frost depth. The expected frost depth should be established using local records, experience building practices. If there is unavailable use of the procedures of TM 58526 AFP 88.9, Chapter 6, alternate frost depth procedures. If the procedure can only be used in grain soils of relatively uniform compensation, different depths. Determining the air freezing index, the number of days above and below 32 degrees between the highest low points of cumulative degree day curved freezing season. For the decision of the air freezing index, use the 3 coldest years in the last 30-year record. Using an average index multiplied by 1.75, fewer than 30 years of the data available for the area freezing index's coldest year is in the last 10-year period may be used. If the local year records are unavailable, use values directly for either Figure 615 or PK's World Index Program. This is the design area freezing for the North America. Design frost depth at Figure 616. The greater gravel thickness is figure is total depth of the ballast, sub-ballast, multiply the frost penetration. Value of 0.16, resulting in number smaller than the greater than gravel thickness. Adequate amount of ballast and sub-ballast in the cross section. Larger additional ballast, sub-ballast should be added and thickness recalculated. Air freezing index, surface cover, frost penetration relationships. Bare ground, snow free, and frost penetration feet. Well drained, sandy gravel, thickness of gravel overlying silty soil, no gravel, 1 inch, 1 foot, 2 inch, 3 foot, 1 foot through 10 inches. Alternate design procedure. An alternate method of designing effects of the frost is reduce effective strength to avoid compensating the thaw weakening period, similar to reducing strength of the pavement design. Methods of reducing frost effects. Additional ballast, sub-ballast impart more than 40% of the total frost depth of the frost susceptible grade. Non-frost susceptible materials clean. Ballast, sub-ballast must be added to the roadbed. Geotextiles can be used preventing particle mitigation of subgrade and sub-ballast interfacing during the spring thaw. The combination of otherwise cleaning ballast, sub-ballast, subgrade soil can turn the non-frost susceptible material into the frost susceptible material. The application of geotextiles is in TM 818A, AFMAN 32 8011. Installation materials. Frost heaving must be reduced and eliminated by using installation materials. Material are useful areas of deep seasonal frost, lack non-frost susceptible soils, areas of subgrade soil conditions that may be differing, heaving and expanding. Extruding polystyrene foam boards are two most commonly used synthetic installations. Extrude polystyrene is generally most popular. In some instances, organic materials such as peat bark or wood chips, timbers, or mineral materials such as slag or gravel has been used. Placement of other insulation can be between the ballast and subballast in the subgrade, anywhere in the between. However, the insulation should be placed deep enough for the cross section to prevent damage to by maintenance equipment. In general, minimum depth of 24 inches in recommended results of the field and laboratory has been shown. Extruded polystyrene retains the thermal properties, do not absorb a significant amount of moisture as used if a board is protected from deformation. Their thickness is covered for the installation, usually determined vertical stress and caused by the dead live loads and limited 1/5 of the comprehensive strength of insulation material. Extruded polystyrene available comprehensive strength of 4 to 6 psi. Physical properties available in thickness and sheet sizes available for the manufacturer specification. TM 5852 AFM 8819. Chapter 6 provides calculation of frost depth where insulation is used. H. Transition zones. A gradual transition is required between the areas of significantly different frost heave behavior. The transition to distributes differential heave and other distances that reduce different determinal effects. The transition between the cuts and fills and the culvert crossings bridge approaches that are typical 75 to 100 feet long. Construction procedures. Subgrades will be excavated, scarified, and predetermined depth based on the field conditions and the wind road and bladed to achieve the adequate blending. They help and ensure the high degree uniform soil conditions, eliminate and insulated pockets of soil higher than lower frost susceptibility. It may necessary to remove the isolated pockets or either low, high, or frost susceptible materials. In these cases, they should be evacuated to the lost frost depth replaced with the surrounding soil. Stones 6 inches in diameter or larger, large routes must be removed to any of the fill depth of the frost penetration. This includes any stones encountered during the subgrade penetration. Failure to remove these items can result in thickness, roughness, and stones and routes and gradually heaved upward. A rock excavation passive if drainage should be supplied so that no pockets of the water are left in the zone of freezing. Irregularity as isolated pockets may lead to non-uniform heaving. At the transition between the cuts and fill section, the transition section should be used. The previously discussed frequently rock joint fractures are full of frost susceptible soil. Rock joints and fractures encountered with the subgrade should be cleaned out into full depth, frost penetration. These joints replace the non-frost susceptible material. 10. Drainage. Important, although not a component of the track or roadbed, drainage or lack of it can have major impact on the track strength and longevity. Without proper drainage, the track will fail to perform the design intended. B. The design of TM 820-4, AFP 88-5, Chapter 5 will be used to design design structures except for modified in following paragraphs. Side ditches. Most commonly, drainage approved for the operating of the ditches running parallel to the track terminal and other areas. The subgraded sub-drainage, alternative drainage will be required. To prevent significant loss of strength in the subgrade side ditches, there must be provided ample capacity flow rate. The side ditches will be based accepted when the rainfall runoff and the contribution of other drainage to the empty of the ditches. Guidance of estimating runoff ditch size may be found in TM 5820-4. To provide adequate capacity, side ditches will be designed at 10-year storm. To provide adequate flow rate for the minimum gradient of side ditches of 0.30%. While not desired practices, there are some ballast sections that cannot be installed raised or surrounding ground level. Standard side ditches cannot be dug or would not provide sufficient flow. In these cases, sub-drainage will be installed. This is a required sub-drainage where the open and side ditches can be installed. It shows the wood tie with a 4-foot 8.5-inch gauge from the center, 12 inches off the type, with a heavy geodextile 12 inches on a 5% slope to the minimum with a granular filler tube where they have a provided type adequate to fulfill the fall to drain. Culverts, Chapter 1, Part 4, Chapter 8, Parts 9, 10 and 13. The ARIMA Manual provides design criteria for specification of railroad culverts. All culverts will be conformed to the current ARIMA ASTM recommendation specification culvert and under the railroads. A minimum cover 2.5 should be provided at the bottom tie at the top of the culvert. 11. Geotextiles. Application under the track. Geotextiles are some used under the track provided filtration or separation ballast, subgrade of the ballast, sub-ballast, drain functions. Common location and installation geotextiles under the track are 1. Highway railroad grade crossing location of poor subgrade when rebuilding track of historic history, excessive loss of profile surface, frequent track of the maintenance requirements. Turnouts in Figure 618, bridge approach to 619, rail crossings. Recent industry studies show that the geotextiles not always have been effective under track, thus in deciding to install geotextiles, thorough analysis of the site must be done to ensure that the geotextile accomplishes intended purposes. Figure 618, geotextile installation under terminal. It shows the ditch drain side drainage with at the switch point with the ditch drainage, geotextiles at the drain to the side of the rail, meeting up at the ditch side of the drainage at the turnout. Geotextile extended at least 25 feet from the heel of the frog. Geotextile installation on a bridge abutment. You see the rail and its ties in a cross section where it shows the geotextile 12-inch minimum drain, a perforated pipe holds down providing the drainage to the side of the ditch, geotextile extending a minimum of 50 feet of the abutment. Material installation specification. Geotextile installation will conform to specifications Chapter 1, Part 10 of the ARIMA Manual. Design guidance is TM 5818-8 will be used to design geotextile applications. Drainage applications lighter weight. Geotextiles are often useful for drainage applications outside of the track structures, especially in subgrade. Ballast. The purpose of the ballast is 4 main primary functions. Distribute the wheel loads, reduce pressure to the subgrade, restrain the track laterally and longitudinally, help maintain track surface, allow the track to structure to drain. B material. As a ballast depends on high friction interlocking, be effective restraining track. It must also be withstanding large load, and ballast must consist of a hard angular crushed rock and crushed slag. Common rock material suitable for the ballast: granites, the trap rocks, quartzites, dolomites, hard, and limestone. Limestone degraded the tend to produce the fine particles of the cement together, and/or that is not ballast choice. The hard rock material, economic of the available crushed slag, can also vary greatly in quality and suitable with a good ballast. 2. C. Graduation. Table 6.8 recommends the ARIMA ballast graduation for the main running tracks. The sizes 4A and 4 will be used. The loading track at the terminal area. Size 5 may be used on facilities. Easier walking along with the car during loading and unloading operations, but its large size is preferred with long track maintenance. The ARIMA ballast graduation of 4 is identical to the ASTM C33 graduation 4. ASTM C33 graduation 56 is closer to the ARIMA number 5. 4A has a nominal size square opening of 2 to 3 and a quarter inch, 2.5 inches at 100% of the weight on a finer than each, 2 inches at 90 to 10% of the weight, 1 and 1/2 inches to 60 to 90% of the weight, 1 inch 10 to 35, 3/4 of an inch 0 to 10 inches, and 3/8 of an inch 0 to 3. The size of the running track at 4 has a nominal square and opening of 1 and 1/2 inch to 3 1/4 inch, 100% of the weight at 2 inches, 10 to 90% at 110 1 1/2, 20 to 25, 20 to 55% at 1% of the weight. Amounts finer than each sleeve square opening. 3/4 inch, 0.15% of the and 0.383 of 0.0 to 5. Size rail number 5, which is ASTM CS33 graduation 56, close to the ARIMA area number 5. 1 to 3/8 of an inch, 100 at 1.5 inch, 90 to 100 at 1 inch, 47 to 75 at 3/4 inch, 1/2 at 15 to 35 inch, 3/8 of an inch, 0.15, and number 4 at 0.5 inches. For smaller projects where less than 200 tons of ballast is needed, where nearest suppliers do not stock ARIMA graduation, the following ASH TO highway graduations may be substituted CAFA, ARIMA 4 and 4A, CA, ARIMA 5. The depth. The depth. Appropriate ballast will be determined in structural analysis using computer programs specified in paragraph 6. The manual method described in paragraph 7 may also be used, not preferred to all cases. The minimum manual ballast of the bottom of the subgrade will be 8 inches in most common cases. However, the main running track will require more. The cross-section of figure 6.1 and 6.7 and show standard ballast shoulder widths and slide lobes finish and resurface track for the top ballast, and may be up to 1 inch or below the top of the tie, never above the top. 13. Subballast. Subballast is a layer of material between the top of the ballast subgrade graduation finer than the top ballast of the coacer of the subgrade. The subballast is often cheaper than the top ballast, so in the case of the B, you reduce to the top of the ballast cost of the provided filter between the top of the ballast and the fine grade subgrade. Figure 6.4, 6.4, 6.2, 6.4, and 6.5 should be subballast layer. The application of subballast for recommended in new construction is in addition to providing the keeping subgraded particles working in the following ballast and providing good mat end to the distributes the loads of the ballast, preventing the ballast particles and being pushed into the subgrade. A subballast layer is required whenever the subballast contains 85% or more by weight of slit and clay sized particles. The subballast the subgrade materials have a liquid limit greater than 50%, plasticity increased greater than 20%. Material subballast should be harder and angular, non-cementing material, primarily sand-sized particles. Gradation. The function of filter layer subballast particles should be ranged in size of smallest ballast particles to large subgrade particles. Over the clay and silty clay, the greater 85% passing of the number 200 sieve. The following gradation recommended: the sieve size of 1/2 inch, percent of 100, 3/8 of an inch, 90. Number 4, 80. Number 10, 70. Number 20, 50. Number 40, 40. Number 120. And 210. The graduation can be approximated by the ASTM D1241 graduation C and somewhat finer graduation. Over the subgrade within more than 15% of more than 200, either than the following should suffice: subballast of the AAS HTO graduation C 19 ASTM D1241 graduation C. Depth. During the structural analysis, subballast layer is considered as part of the top ballast depth. The subballast layer must comprise up to 40% of the top ballast depth and may run tracks of the up to 50% of the auxiliary terminal tracks. When used, the minimum subballast thickness will be 4 inches when minimum total ballast depth is 10 inches. 14. Ties and spacing material. In most of the cases, wood is the most cost-effective material. Wood ties meet the requirements of Chapter 3, Part 1, ARIMA Manual. Recommended species of wood across the ties: hardwood, softwood, ashwood, dogwood, fir, beech, pine, hickory, spruce, red oak, and white oak. Strictly defined hardwood and softwood referred to is to trees and not hardness density of the wood. However, the hardwoods listed above the denser, generally more durable listed softwoods than usually desirable ties. When the softwood sometimes preferred an open deck bridges help absorb impact, they recommended for the use of turnout sharp curves over the degrees of the better spiking holding ability. Denser wood is needed. 3. The hardwood is ties often species groups of such mixed hardwoods, oaks. The mixed hardwoods comprise, for example, 40% of oak, 60% assorted hardwoods, including gum. Gum is not preferred as specified. Commonly used, the oak group is usually mixed with a red or white oak, typically costs more than the mixed hardwood. For the track annual traffic volumes to 5 mgt, less than commonly military insulation wood ties, more likely to fail, decay, rather than mechanical wear loss, spike holding ability. In such cases, the selection should lean toward the available species readily accept the deepable penetration preservative treatment information of the engineering department of the service commercial carrier for regional tie space suppliers, and local experience should be helped in the selection of the most appropriate ties. Cross-section and length. The two common cross-sectional sizes of the wood track are 7 inches thick by 9 inches by wide, or 6 inches thick or 8 inches wide. That's basically your tie plate size. 7-9 inches recommended areas of high traffic volume, while the wheel loads are the turnout and railroad crossing. Track ties are commonly produced by 8.5 to 9 foot lengths. 8.5 length will be used most conveniently available. Ties turnouts vary to the 9 foot to 16 foot long will be also indicated in the table in 6.9. Switch ties and standard turnouts. You have your frog 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 16, 18 to 20. It skips 13 and 17 and 19. The switch point length is 16.5 inches for a number 7 frog, 62 lead distance 62 feet 1 inch, 9 number of ties of each length, 9 foot ties, 13 10-foot ties, 11 foot 6 foot ties, 12 foot 5 foot ties, 13 3 foot ties, 14 4 foot ties, 6 15 foot ties, 6 16 foot ties for a total of 55s. The Frog 8 has a 54 total ties. Lead distance is 68 feet. The switch point length is 16.5. It's 9 foot 7 9 foot ties, 10 foot 13 foot ties, 11 6 foot ties, 12 6 foot ties, 13 4 foot ties, 14 5 foot ties, 15 feet 7 ties, 16 feet 6 foot ties. Alright, 7 through 10 have the 16.5 inch switch length. I'd just say print this out when you get a chance, but like we're gonna go over the parts. Each tie sets 2 or 15-foot ties have head blocks which hold the switch standing. Treatment. All wood ties are pressure treated with preservatives specified below. The preferred preservative tie creosote solution of 60 to 40 specified by the AWPA standard P2. For the ties used in the Mississippi River, the creosote type petroleum is 50/50 specified AWPA standard P3 may be used. Anti-splitting devices to reduce tendency of wood to splitting. Anti-split devices often applied for the end of the ties. Anti-splitting recommendation for the turnout of ties must be specified for the standard track ties. Other two general types in Figure 6.2, the nail plates are more effective than thus preferred. These are anti-splitting devices for the tie ends. You see the nail plate and the S's and the C irons. Reboring on the most common practice. The pre-boring of the spike holes is no longer the recommended. Tie spacing of the center distance between the adjacent ties will usually range from 19.5 to 22 inches minimum allowable, 18 inches maximum, 24 inches. Auxiliary loading tracks of 21 to 23 inch spacing will often suffice. Tie spacing will be spaced after structural analysis and has been performed. Concrete and non-standard ties. Concrete ties are used in commercial railroads, particularly on lines of heavy traffic volumes, areas with numerous curves. When using concrete ties, track the welded rails solidly supported the deep ballast sections. Concrete ties usually not economical or lighter traffic lines, usually not sustainable with the joint rail or track or lighter construction. Also, concrete ties cannot be successfully mixed with wood ties. The concrete ties are not recommended for general use in military track. The use of concrete ties for the certain special application must be cost-effective. The benefit of the installation must be thoroughly investigated prior to the selection of the concrete ties. Research development continues of the ties made of alternative materials of hybrid construction, none of them yet proven economical, routine, or general purpose. Rail. 15. Rail. Section designation. Rail is rolled in different sizes and dimensions, shapes, and commonly referred to as weight and section. The weight of the rail is based on how much the rail weighs and per pound of the yards and of length. Section refers to the cross-sectional shape of the rail. Selection criteria. For the selection of rail selection will be done, but the structural analysis has been performed. Designer will be determined structural requirements as well as cost availability performing rail sections before financial selection is made. C. Recommended new rail section. Weight of the section recommended the new rail purchase of 115 RE, 132 RE, 133 RE, and 136 RE, and 115 RE being preferred. There are standard sections recommended by the REMA and should be available for many years. Rail may be purchased in 39 or 80 foot lengths. A rail 80 foot long has the advantage of reducing the number of joints to half that of a 39 foot length. For small purchases, rail may be transported to the truck. 39 foot length may also be cost effective. Relay. A second-hand rail. A second-hand rail meets the specification in Table 610 either by the cropping off of the ends, maybe rehabilitation, new construction before the selecting of the relay railing, cost, condition, availability, matching joint bars, tie plates investigated. Dimension surface specification relay second-hand rail. Length for the standard length of 39 inches, more than 10% of the lot, between 10% of the lot between 33 foot and 39 foot. No rail shorter than 33 foot. Vertical wear 90 pounds or larger. Average wear of 5/16 of an inch less than maximum at one location of 11.32 of an inch less than 90 pounds. Average top of the wear of 1/4 of an inch less than minimum of any of the location of 9/32 of an inch. The side wear, at least one side of the must be the following: 90 pounds larger, minimum 5/16 less than 90 pound, maximum 1/4 of an inch. Lipper overflow, maximum 1/16 of each. Either is obtained by the grinding of off excess. Engine burns, maximum of 1 inch of the diameter or 1/4 inch wide with 1/2 inch long or 1/32 inch deep. Maximum 4 engine burns per rail. Engine burns no more than 80% of the lot. End batter and chipping, maximum 1/8 of an inch when measured 1/2 an inch of the rail ended with an 18 inch straight edge running surface. The maximum size of 1/4 of an inch wide by 1/2 an inch long and 1/32 inch deep. Maximum 4 damaged spots in any one rail. Defects, permits, bolt holes, brakes, broken bases, crushed head, detail, engine burn, fractures, head web base separation, piping, horizontal, vertical, split head, web, torch cuts, flammable gouges, compound, transverse fissures, deep hitting for corrosion. Condition rail must be free of obvious defects, cleaning appearance, straight line surfaces without kinks, and are free of the base of the defects such as plate wear and spike notches. Internal inspection. Rail the ultrasonic inspected before and after all installations. Defective sections may be rejected and replaced. Note: see ARIMA Manual Chapter 4 Part 3 of the rail defecting definitions instructed. 2. Recommended relay rail section 100 ARAB, 112 RE, 115 RE, 130 RE, 132 RE, 133 RE, 136 RE. Relay rail should always be selected limited in the number of the different railway sections within the track network. For given weight of the section, rejoint drilling patterns, bolt holes, sizing, and spacing should be also consistent. Due to the varying of the market of the relay rail, it may be beneficial to allow the contractor option to provide acceptable rail selection should be limited to the section sufficiently plentiful supply. Further maintenance purchase requirements, rail joint bars, frogs, and other turnout parts. Lightweight rail weighs on the 90 pound per yard. The weight of no longer manufactured are unavailable in secondhand. For the main running tracks, the railway weighs less than 90 pound per will not be used. The railway weighing 75 pound per yard or 85 pound yard may be adequate for terminals auxiliary with light use, depending upon the support conditions. The structural evaluation necessary to determine if the adequacy of the railway weights or rail not adequate to support desired wheel load should be replaced. F. Continuous welded rail. Continuous welded rail, CWR, is string line standard rail welded together in either rail plant or welded fielded welding after installation. This continuous welded rail is commonly used in commercial railroad and beneficial, reducing maintenance and cost due to the rail joints. Continuous welded rail is recommended for the general use of the military track because it requires large ballast sections to provide sufficient track resistance. 2. Needs more than rail anchors to restrain longitude rail expansion. 3. Is more subject to buckling, hot weather, and pull aparts during cold weather. 4. Has higher initial installation costs and convenient availability. Short strings less than 200 feet and may be appropriate for the wide range crossing track and paved areas. The continuous welded rail have good application in certain lines and long connections serving commercial carrier. The field welds. It is recommended the rail of the road crossing and 20 feet of either the side of the crossing be welded, eliminating joints in these cases. Likewise, the field welding should not be considered the rail placed in combined loading areas, adjacent warehouse, loading docks, and other areas of maintenance. Excess rail joints will be difficult. Rail welding may only be accomplished by a special thermite welding kit designed for this purpose. People necessary training experience in welding rail, where many welds are done, and some specified contractors have truck-mounted electrical welding units designed for this purpose. Salvaging rail during the railway track. The existing rail and the track materials can often be salvaged with used at locations or on the installation stockpile for further construction projects. Sold on the open market. The use of the material lightweight rail, defective rail, to other truck materials suitable in track reconstruction, installation, resale, open market should be disposed of the scrap and re-roll re-roll material. 16 definition tie plates, joint bars, bolts, spikes, miscellaneous hardware used in the track construction, commonly referred to as the other track materials, OTMs. Tie plates are of varying length and width, and most sizes suitable as long as the spike hole punching for the other distances between the shoulder and double shoulder plates matches wide of the rail base. Double shoulder ties distance between the shoulders that would be almost 1/8 of an inch larger than the rail base. On single shoulder plates, the spike holes on the gauge side open. The opposite shoulder of the shoulder must keep the inside of the base of the spike within 1/8 of an inch of the railway base, the opposite edge of the base against the shoulder. See Figure 621AB. This shows a double shoulder tie plate with 140 and 1/40th ratio, maximum 1/8 of an inch larger rail base con and space. Single shoulder tie with 1/40th ratio rail, maximum 1/8 of an inch space from the center of the track. Either single or double shoulder tie plates can be used within a given length of the track. The tie plates different length and width may be used in single shoulder, may be mixed to double shoulder plates. However, the plates are different cants and those with level rail seats and those of 1/40th slope will not be mixed. The tie plates of 1/40 cant are preferred. Second-hand plates are not bent and they have not been not so much material due to the corrosion. Otherwise, meet the above requirements are acceptable. Spikes on tangent tracks. Curves up to 4 degrees on a spike. The gauge field side of the rail will be used. A total of 4 spikes in each tie. A curves greater than 4 degrees on a spike on the field side of the 2 spikes on the gauge side of each rail will be used. A total of 6 spies in each tie. Rail joints and joint bars. Either the 4-hole 24-inch or the 6-hole 36-inch joint bars will be used as rail joints. The standard compromising joint bars properly factored design and construction will be size, shaping, and the punching pattern of the fitting of the bearing being of the joint. New joint bars will be specification high carbon steel joint bars, specification quench carbon steel joint bars, and forged compromised joint bars. In Chapter 4, Part 2, REMA manual joint bars assembly. Chapter 4, Part 1, and REMA manual compromises will be specified in the REMA Plan 700B. Special second-hand joints bars are used in second-hand rail is not corrected, excessively corroded, otherwise defective second-hand joints will not be used in the new rail. 4 insulated joints are required and they isolate the signal currents for the road crossing warning devices may either be field applied a typical field type or prefabricated glue type. The special insulated ties are required. It is recommended rail situation welded located in the road crossing paved areas and any location where the joint is restricted. Track bolts, nuts, and spring washers. Track bolts, nuts, and spring washers will conform to the specification in Chapter 4, Part 1 and 2 of the REMA manual. Common bolt diameters, different rail weights are found in Table 611. A bolt diameter of 3/4 of an inch is a rail weight of the pound in the yard of 60 to 75 pounds in the yard. 7/8 of an inch at 60 to 70 pounds at 90 yards. Bolt diameter 1 inch at 90 pounds at 130 yards, and 1/8 of an inch at 131 and 140 yards. Rail anchors restraints from longitudinal rail movement should be used in the main running tracks and in the quantity arrangement. The diagram 622 is minimum. Additional anchors may be required for the track grades steeper on 0.5 where a combination of track volume, speed, and curvature indicated a need. A low track traffic standard shows the ties and the rail joints with the rail anchors spaced evenly. The rail anchors are large traffic volume on the grade for a large traffic grade. When anchors are used, each type of anchor will have 4 anchors applied with the box anchor per type shown in Figure 622. Each type of anchor spring of the drive-on shown in Figure 623 may be used. Drive-on anchors advantage may be easier to apply. Removable manual do not require a special anchor wrench, and as do spring anchors is possible to overdrive the driver anchors, causing it to lose ability to tightly grip the rail base. Rail anchors, spring, drive-on, and the spring kind of rail anchor and the drive-on anchor. Rail anchors will not be used across open deck bridges. Instead of 2 rail lengths off each end of the bridge, every third tie should be anchored. A similar arrangement should be used with rail crossings. Figure 624. Rail anchors should be applied in normal designated pattern across the ballast deck bridges. This is a railroad application of open deck bridges and a railroad crossing. You say no anchors. 2 railway lengths between box anchors every third tie. The open deck bridge has no anchors, and 2 rail lengths box anchors every third tie. An anchor at the opening of the deck. Anchor of the railroad crossing. Square railroad crossing has 2 rails. Box 3 every third tie. 2 rail lengths. Box third every 2 rails. Gauge rods. Gauge rods are sometimes specified in very sharp curves over degrees of difficulty. Holding the gauge is anticipated when used in sharp curves. 2 and 4 rods should be installed per rail length, and the general use of the gauge rods encouraged should be reversed in special and unusual cases. We're going to come back to 17 turnouts crossovers because I like have turnouts separate.